Good afternoon or good morning, depending on where you are in the world. Welcome to this webinar, which is entitled Smart MPL Solder Paste Printing and Reflow Problems, Causes and Cures. And this is a pre-show webinar, pre-show prior to the SMTA International show. Basically what we're going to be doing during this webinar, of course, is talking about the topic of interest, but also we'll be telling you about what we're going to be doing at the show in a week or so's time. Now, just a little bit of information first of all before we get started. If you want to open or close the control panel that's on your screen, you can do this by clicking on the orange button. This prevents it obscuring your view of the slides during the presentation. You can click on the blue button, and this makes the image on your projection system or on your screen go full screen, thus giving you the best view of the slides during the presentation. If you have any questions on any particular point during the presentation, you can drop a question in the box as indicated here. Although we'll be providing answers to questions during SMTA International, and you can spend whatever time you want with myself and other MPL staff to answer questions specifically for you. Now, if you have any technical problems during the webinar, then please use one of the GoToWebinar telephone numbers provided on your email. You'll also need your access code and reference number. And unfortunately, myself, as the organizer and the presenter, is not able to assist you during a live presentation. There's also a couple of survey questions at the end of the webinar, and perhaps you take a few moments to give your comments on the webinar and its content. We'll also be running a couple of surveys during the webinar, and we'll be feeding that information back during SMTA International. Now, just a little bit about my background. Basically, I'm organizing a special feature at the show at SMTA International in Chicago, and I've been involved in electronic manufacturing all of my working life as a mechanical engineer. Over the last sort of 20 to 30 years, I've been involved in training and consultancy with my own business. Prior to that, I worked in manufacturing, engineering, quality engineering, failure analysis, and environmental test. And these couple of slides just give you a little bit of background about my activities. What I'll be doing at the show this year is two workshops, one on robotic iron and laser soldering, and one covering 01005 and the smaller packages. So if you're interested in that, again, you can follow this link when you get a copy of the slides, or of course go to the SMTA website. So a little bit of an explanation on what we're doing at the exhibition first of all. Now, basically, we have an area within the show, and we're going to be printing boards with solder paste, and then we're going to be inspecting the results, looking at height measurement and volume variations. And we've got a whole range of different components that we'll be printing. And this is an example of the board you see on this particular slide. Now, not only will we be printing, but we'll also be jetting solder paste using the same design, and then looking at the performance that we can actually achieve. We'll be looking at inspecting the boards, the solder paste deposits, both optically and automatically, just to show different techniques that can be used in manufacture. In addition, the area will also have AOI, automatic optical inspection systems, and we'll be looking at a series of boards which have known defects on, so open circuits, short circuits, reversed missing components, modified nomenclature or lettering on the components, etc., etc. So we'll have a series of boards with standard known defects, and we'll be running them through the machines, and you can look at the performance of the machines. In addition, we're looking at X-ray inspection, and in this particular case, we're concentrating on BGAs. So again, we have some samples of both good and bad product for you to examine or look at the results that we get during our exercises within the show. Now, these are our process partners, and all of these companies have contributed either material, equipment, or processes to this particular area, and I'm very pleased and thankful that they were able to support our activity for SMTA International this year. Now, when we talk about inspection and quality control, and of course lots of companies do this today, when we look at a production line and we're looking at screen printing and reflow technology, then there really is just sort of three locations that, generally speaking, we use automatic inspection, or we use manual inspection, or semi-automatic. There obviously is a trend to increase the amount of quality control after the screen printing process to make sure the volume of solder paste is consistent across the printed circuit board. But of course, there are many reasons why we get variability. So if we were to look at this diagram, I've highlighted the three most common places that people use automatic optical inspection or semi-automatic inspection: after printing, after placement, and after reflow. Now, typically, most companies concentrate their efforts after reflow soldering and after the printing process, and those tends to be the two locations. However, some companies may look prior to reflow as well. Now, this is the first opportunity for you to participate in a survey, and what we're going to do is launch a survey, and what we'd like you to do is just take a couple of moments to select which answer you feel is the most appropriate for your organization. Now, each of these survey results will be provided to you again after we've completed the webinar, probably tomorrow morning now, because it's quite late here in the UK. So the first survey I would like to pose looks at what do you feel contributes to your process issues. So all you need to do is select one of those, and I'm just going to take a few moments to allow as many people to contribute as possible, because that obviously gives us the best feedback on what you see in manufacture today. So if you just select one of the items highlighted, so we've now captured over 80% of people participating in this webinar. So I'm going to close the survey at that point, and then I'll move on to the rest of the webinar. There are 3 other surveys, so please take the same opportunity to participate. Now, when we look at the printing process, the key thing with the printing process is making sure that all surfaces are flat and even to get the best print deposit. And here we see just an example of a stencil printing process where we're printing paste onto the surface of the printed circuit board. And then we separate the squeegee blade from the surface of the stencil, and then we lift the stencil off of the surface of the board, leaving the solder paste deposit on the surface. Now, again, there are many variables here. There's the quality of the stencil, the design of the stencil, there's the flatness of the pads, there's the evenness of the plating on the pads or surrounded areas, there is the variability of the solder resist on the PCB, the thickness of that resist, whether you're using resist-defined pads or non-resist-defined pads on your design. So those are some of the sort of key variables, and most of those are kind of outside of the capability of the printing process. So it's not just the printing process that causes the problems, it's the materials and the setup and what we add into the process. And if we don't get successful printing, then solder paste is retained within the stencil. And this can be related to the stencil, the way in which it's been fabricated, or the way it's been looked after. And here's just an example of solder paste hanging up in a stencil aperture after the printing process. Again, a common defect that many of us experience. That is the variability we're trying to monitor when we use SPI, automatic optical inspection, to look at paste deposits. with most of the standard components we use in the industry, slight variability on the volume of paste is not a major issue. And it really is the ultra small packages and the ultra fine pitch where small variability may not allow us to form a solder joint. We need to also consider the printed circuit board, and this is particularly true, again, when we're going to finer and finer and smaller parts. So in this particular example, I'm showing you some small, possibly passive parts being printed. Now, here we've got pads on the surface of the printed circuit board, and the pads are well defined. They've got straight copper walls after the fabrication process. But if, for whatever reason, the consistency of the board fabrication is not good enough, then we can actually get the copper at the top, actually on the top surface, to be a slightly different dimension than on the board surface. So when we actually go through to printing of 0201, 01005 and smaller, the solder paste deposit is not actually in contact with the surface of the pad. It's in contact with the top of the pad, which may be a smaller area than on another pad. And if we look at a close-up of this, we can actually see the pad intruding into the stencil design. And it's not uncommon for design engineers, process engineers like myself, to actually create a stencil which is slightly larger than the pad on the printed circuit board because it makes printing easier. But in this situation, it can actually contribute to problems. And if we're printing onto resist-defined pads, which is popular in many companies, again, the key thing is consistency of height, making sure the stencil is in contact and not deformed in any way. Resist-defined pads can work, but again, it's down to the quality and consistency of the printed circuit board and the suppliers of that. So if you just have a look at a couple of examples of solder paste stencils. Now, I'm sorry to say that these are actually examples where I visited companies and done quality audits. And these are actually some stencils actually taken from the storage area and not actually being used in production. And really, this is very, very poor indeed. So whenever you're looking at visiting a vendor or looking at your own manufacturing facility, make sure you can clean a stencil effectively. And possibly there's a benefit on having some form of semi-automatic cleaning process as part of your process to guarantee that when you do clean a stencil or touch up a stencil, many of us do on a line, that it's effective in the way in which it's removing solder paste from an aperture. Ultrasonic energy has been used as an assistance for a cleaning process over the last few years in quite a few manufacturing facilities in Asia. Now, of course, the stencil is key, and personally, in a manufacturing environment, I always have a backup stencil for anything that I do. I have one stencil that I'm going to use and a backup stencil if something goes wrong. Now, I know all good stencil manufacturers can give you a one-day spin, but having a backup stencil today, where the cost isn't as significant as it used to be, I think it's beneficial. But these are just examples of stencils that should not be on your line. I hope that none of them are like this that are on your line. But you can see they're either coined, that's deflected away from the print area. The separator parts are deformed or broken. And in the one case on the bottom left, you can actually see a laser cut stencil where part of the aperture is still actually in the stencil. Not a very good example of quality control from the manufacturer. Now, if we look at some simple process problems with solder paste and printing, I've given you some very simple ones here. First of all, we've got scooping on the top left. And this is literally where you've got either too big an aperture and too high a pressure, and you're literally drawing the solder paste out because the squeegee blade, even a metal blade, can scoop down into the aperture if you have too high a pressure. On the bottom left, This is to do with the stencil separating unevenly from the surface of the printed circuit board. And what it's doing is leaving some solder paste deformed and some solder paste still left in the aperture of the stencil. The same sort of fault is seen on the top right-hand image. On the bottom right-hand image, you can see a wet deposit, what I refer to as a wet short. So where you've got solder paste which is shorting between fine pitch, which may or may not cause a short during reflow. If you look at this example, probably the examples on the right-hand side where you can see a very minor wet short probably won't. But the one on the left-hand side of that particular image will cause a short. So again, it's deciding on what is a quality problem where you need to wash off and reprint the board or not. Now going on back to the examples I talked about for ultra-fine pitch, these are examples of boards, process boards, test boards that I've been running most recently. And you can see on the left-hand side incredible over-etching where the tip of the pad is much smaller than the pad area in contact with the surface of the board. Now these were trials on the smallest chip resistors and capacitors currently available in the marketplace. And I've listed Rome, Urata and Panasonic as some of those suppliers. The photograph, the microsection that I show on the right-hand side is examples of good pads. Yes, there is a slight difference in the dimension between the foot of the pad and the peak of the pad with this nickel gold board, but this printed successfully, whereas the other board on the left-hand side was unsuccessful in the print process. Now, if you look at these two examples, this is not uncommon to the challenges that we have with ultra small components. And what you can see here is a small daub of paste on the left-hand side, which is misaligned. Now, alignment of a printed circuit board and the stencil to it are key, but some of you may not be aware that when you reflow a printed circuit board, the dimension can change. So when you do second side reflow, the actual physical position of the pads in relationship to your stencil, your design stencil, may not actually be in the same position. The reason being that moisture in the board has been taken out to some degree and it changes the dimension of the printed circuit board. That's why a lot of printer manufacturers have quite sophisticated software to try and accommodate this particular problem. However, you can't change a stencil dimension. You can change the position of the stencil in relationship to the board, but there is a sweet spot that you might be able to find. The second example on the right-hand side again is misplacement of the paste deposit onto the resist and laminate, but you can actually see on one of the pads where we've actually got some coining of solder paste, and this was probably trapped underneath the stencil. So when you're doing ultra fine pitch and ultra small aperture printing, the number of cleaning cycles that you should conduct on the underside of the stencil has got to be considered in detail through obviously the trials that you're going to conduct. Now I highlight again this very small passive component. We can get to a situation that we can actually lose pads. On the left-hand side, you can actually see that through the over-etching on these particular samples, we actually lost pads. And I can remember doing this a few years back with 0201, where even with the pressure applied during the etching process, we were losing some of the copper geometry through the fabrication process, which theoretically shouldn't happen today, but clearly we've got a good example. We managed to get a daub of paste, perhaps not in the right place. On the right-hand side, again, you can see coining on the surface with virtually no paste present. Now, some years ago, I produced a set of inspection and quality control standards for paste and paste application on printed circuit boards. You know, this is an example of small passive components. This is SOT 23s, and the next example is for BGAs, and these have been available for some time. We created this when we set up in the UK the PPM project, where we were monitoring PPM levels on screen print, placement, reflow, and other processes. And at that time, there was no criteria for paste deposits. everybody probably had their own view, but we needed to have something to measure by to do some sort of assessment. Fortunately today we have a standard. The IPC 7527 has some basic criteria for paste deposits and coverage on the printed circuit board. So we'll have a couple of these documents in the feature area of the show for discussion if you're particularly interested in inspection and quality control and some basic standards that exist within the industry. Now, just a couple of more printing problems, and these really are all typical examples of alignment. Now, again, we've got 25 thou pitch, 50 thou pitch, and some small passives and a SOT23. But these are all alignment issues. And with the automation we have today, really the alignment issues should not be a problem. And one of the other things I like to highlight to people is to always try and never print a board unless you're 100% happy that you're going to get an even print. Now, the reason I say that is because you can use plastic film that's applied to a printed circuit board and print directly onto that. So you can do test prints prior to actually doing printing onto the board. The reason is that we want to try and avoid wash-offs wherever possible. Wash-offs can affect the wettability and solderability of the printed circuit board if not done correctly. So whatever we can do to minimize wash-offs, i.e. print defects and reworking of boards, that's got to be a good idea. Another example of misalignment, again, this is a 20 thou pitch on the bottom image, and on the top image we're looking at some small passives. These are 0201, and this is one of the first boards that we were doing when we noticed the variation from side 1 to side 2. And again, a lot of engineers are pretty much aware of this today, but it's something that perhaps a few years back it was not so apparent. Certainly in Asia, there were quite a few large companies that were doing pre-bake of all boards prior to the first reflow to make sure they got the correct alignment, and then there wasn't so much variation on side 2. So it was nothing to do with getting moisture out of the board because of delamination or outgassing or something like that. It was all to do with the alignment, and there's some very good technical work was done on that particular project. Now, if you would like some copies of the IPC standards, we have them up for grabs. So anybody visiting the feature area at SMTA International, for the best questions of the session, best questions on process defects or anything to do with the printing and reflow inspection, we have sets of standards available, and again you might have the opportunity of winning them at the show. Right, time for another little survey, and because we've been talking about the printing process, what I'd like to do is ask you some questions about the printing process. So please, if you would like to select out of these examples what you feel is the most common reason for getting soldering defects in your process. So if you'd just like to take a few moments to complete, all you need to do is click the button, select one of the items here. And I'll just give you a few moments so we get up to a really good percentage. Excellent. We're over 90% now. So what I'm going to do is stop the survey, and we'll move on with the webinar. Now, one of the other things that we're featuring at SMTA International is the Defect Database Live. And it's your opportunity, if you wish, if you're coming to the show, to bring along some sample boards, process problems, issues. Obviously, we're featuring and talking about printing and paste and reflow technology, but both myself and Dr. Chris Hunt will be there and more than happy to answer any questions on any process issues or process problems you have. All I say is buy me a cup of coffee, bring it along, and I'll be sitting there and I'll be more than happy to spend some time with you. So that's the Process Defect Database Live. Or if you've got a specific problem and you want to email it in advance, the email address is available. My SMTA email address is available on the slide. So when you receive them, you can mail it in advance prior to coming to the show. Now, if we talk about reflow soldering, there are basically two processes that we use within the industry today. There's convection reflow, where we're reflowing in air, or alternatively, we might be using nitrogen. The vast majority of people that do convection, even for lead-free, are still reflowing in air. There are a lot of companies using nitrogen, but the vast majority use convection in air. And the other process, which for younger engineers, it's new to them. For older engineers, you've seen it, done it, been there before, is vapor phase. And vapor phase gained popularity during the introduction of lead-free technology and has been gaining more and more popularity. And basically, vapor phase is a fixed process. You have a fixed temperature. You cannot exceed that temperature. You can leave the boards in for too long, but you're not actually exceeding the peak temperature of the fluid. Now, the other benefit of both of these processes is you can also use vacuum if you wish. And the reason that there's a lot of interest in the use of vacuum with convection reflow and vapor phase reflow is to reduce voiding. So you can remove voiding under LGA QFN packages, from BGAs, from very large packages, QFN packages, and others. And that is perfectly feasible to do, and you can do it. You've got to then consider what the downside of that is. And the downside, generally speaking, is throughput. So there is an impact on throughput capability with either of the processes if you're going to use vacuum. So you have to decide whether you need to eliminate the voids, whether they are as significant as you think you are, but it's something you can do after you've exhausted all of the other options. The other options that we have in our industry is obviously looking at different pastes, but the key thing is finding out why you've got voids in the first place. So these are just typical profiles, example profiles. So you can actually create a profile for vapor phase which pretty much looks the same as a convection process if that's what you want to do. Now, if we look at introducing vacuum into a process, typically you can either introduce vacuum just during or just prior to going into a liquid state. So we can have vacuum introduced while the solder is in a liquid state. So you're literally sucking out the voids. And if you actually look at this in X-ray and video it, you can actually see this take place. You can run a vacuum system at other parts of the process as well. So again, you've got the flexibility. With convection reflow, generally speaking, you can only run the vacuum just prior to or in a liquidous state, so in the liquidous zone, in one of the three zones you might have at the end of your reflow process. Again, you can reduce and improve the yield in terms of voiding if voiding is a major issue to you. So that's one variable that a lot of companies are interested in right now. Now, one of the things to bear in mind and think about is why we have voids in the first place. And certainly under QFN packages and LGA packages, you know, one of the reasons that we have a lot of voiding is there is a lot of solder paste which is present underneath these packages. And these two video clips basically show the reflow process. On the left-hand side, you can actually see now the solder paste volatile material which has come out from underneath the package. On the right-hand video, you can actually see the package sort of dancing up and down, bouncing up and down. And this is because there's a lot of volatile material coming out from underneath the package. Now, of course, we can reduce quite significantly today the amount of solder paste we put on the center slug or the heat dissipating area on one of these packages. And that's really what you've got to look at, how much you can reduce the volume that's there. And then the next thing is to try and evaluate a solder paste which minimize the volatility which is left when it's in a liquid state. Those two things need to be done to reduce voiding, and if you can do that, that's fine. If you can't do that for whatever reason, then you need to look at another option. So let's just look at an example while we're talking about vacuum. And here I've got, first of all, an X-ray that I've taken of a package, a transistor package, and basically you can see it sitting on solder paste. So this is prior to reflow. And then what I've done is I've taken a board with these devices on and reflowed it in convection and also reflowed it with vapor phase. And really, there is no difference. There's no significant difference in the amount of voiding which is present. So we may be able to optimize the process to reduce the voiding. And that's one thing we can obviously experiment on, but it does take a lot of work and effort to do this. Or alternatively, if you're particularly buying a new machine, then you can look at the option of using vacuum. So what I show you here is just one example of vapor phase with vacuum with virtually no voids. And I've done this with convection as well, but I just show the variation that you might see between the results. But the key thing I would always say to people is, are the voids a real issue to you to start off with? They're sometimes an issue to a customer who's working with a contractor, but really, in all honesty, 9 times out of 10, it's not really a major issue. Now, voiding can obviously create voids within solder joints, but there are other reasons why we get voids and cavities during a reflow operation. So although we blame the paste or blame the profile or one of these things, always think about what you're soldering to. And here I've got 3 video clips that I wanted to share with you. And the first of all, what we're showing here is a pin with tin plate on, and we're basically reflowing the tin plating. And even online with this sort of sluggish video, you should be able to see the gassing from the surface. You can actually see bubbling on the surface of this particular pin and some de-wetting. On the second video, on the top right, again what we're doing is a video simulation, and what you can actually see is gassing from the plating on the surface of the component. And the reason I'm showing you this is just to highlight that it's not always the paste, it's not always the profile. On these 3 examples from my library, I can demonstrate to you that the component was the root cause of the voiding issue. If we look at the bottom left now, and this is just a chip capacitor, if you look at the surface of the plating on this capacitor, it's going through the reflow cycle. We're not looking at where the solder joint is forming, but you can see quite nicely the gassing from the surface of the plating. So again, perhaps one particular supplier was causing a problem more than the other. And the final example is probably the worst example of poor wettability or poor solderability on some pins that I've seen in a long, long time. Now you can see that completely wet and then de-wet completely. So that wouldn't really probably be a voiding issue. I think it would be we haven't formed any solder joint whatsoever. Now open connections are probably one of our biggest problems. If we've got shorts on most components, not all, it's a fairly minor thing to remove. Obviously shorts underneath BGA or LGA packages, but opens or intermittent joints can be an issue. And one of the important things you've got to try and learn is when we're looking at X-ray to try and understand whether we've got a joint or whether it's actually an open. So what I've done here is put 2 side by side, and you should be able to interpret from what I'm showing you the difference between the joints. Clearly we've got an open intermittent joint on this area array LGA QFN type package, and one of the biggest variables I find on this style of package is that companies don't control their downstop. So when they're placing components onto the printed circuit board, they tend to overplace and consequently displace paste, and then it reflows. Some of it moves away from the pad area, so you haven't got the same sort of volume. So any indication of stray paste or small solder balls away from pad areas are an indication of overplacement pressure 9 times out of 10. This then may lead to open circuit interconnections potentially. Now if I look at here, this is a beautiful example of a very bad product, but what you're looking at here is somebody who really had no control of the downstop. So they displaced paste away from the pads, they reflowed, and we've got what some engineers, certainly in the UK, refer to as solder sausages. I don't know who dreams up these names, but you know, that's clearly what we've got. We've got solder protruding between terminations. We've obviously got some large voids. So take care with any area array LGA type package that you've got control of the process, you've got a consistent volume of solder paste, and you don't squash it when you're placing components on to the surface of the printed circuit board. Now, another thing that we started to see during the introduction of lead-free technology is, more examples of copper dendrites or corrosion. Now, I have to say, a lot of people blamed the new materials, and lead-free flux was bad because in all honesty, a lot of it was due to poor profiling to start off with. Just like with wave soldering and selective soldering, if you don't introduce sufficient heat as part of the process of reflow, we can actually still have some material which is present, which is still volatile potentially, and also can be conductive if exposed to voltage and humidity. And these 3 examples here are basically the same image, if you like, but I thought it was worth showing you this as a failure analysis example. First, top left is standard X-ray image of a dendrite, and you can see this with standard X-ray. The one in the center is with no equipment whatsoever. I've just taken a printed circuit board and I've ground up through the board through to the back of the component, and I can see the dendrites. So that's a fairly crude but very simple failure analysis technique. The third technique I've used is standard X-ray, but also using 3D and 3D modeling, so you can see exactly the same thing. So dendrites and short circuits on products, and particularly under packages in conformal coating, can be analyzed with X-ray. It's a lot easier if you know where you're looking to start off with. If you're looking across the whole of a printed circuit board, that wouldn't be the right technique. But I find a lot of companies suffer from problems of dendrite formation, particularly on selective soldering, where they haven't got the preheat right. And if you do SIR testing, you quite often find that part of the process contributes most to problems if you haven't set up your process correctly with the materials from your supplier. Now, solder wicking is kind of an old defect, if you like, and the reason I say that is if you look at top right, I used to run the Texas Instruments SMT workshops in the UK and Europe. There was another gentleman who used to run it in the US, but I used to run them in the UK, and these are examples of wicking. Now, wicking, taking solder away from a surface, can be and was attributed to a lot with vapor phase in the early days. However, it's all about speed of wetting and time to wet. If you've got a solder joint, and if the solder wants to wet the component before it wants to wet the pad, because there's a difference in solderability, then that could be a heating problem because the board is slower to heat up than the component termination, which is normally what you used to see in vapor phase. However, in 2 of these examples, the middle sample and the one on the right-hand side, this is clearly a PCB wettability solderability problem. So the solder has wet up the termination on the SO resistor network because the solderability of the board was affected. And the second example on the right-hand side, again, same basic thing. Again, it's a wash-off. Somebody has cleaned off previously printed paste and they haven't done it correctly or left some residues behind. Hence the problem that we see in this example. Now, solder wicking can also be related to heating, it can be related to vapor phase reflow, and it can also be related to convection reflow with nitrogen. As an example, if you're running a product and you tended to see a lot of your paste volume, your solder volume, being sucked up the pins, sucked up the legs, as you see in these three examples, and you were running convection with nitrogen, all you need to do is reduce the quantity of nitrogen, i.e. dirty up your process. You'll save money on nitrogen costs, but you won't get the same speed of wetting, the same degree of wetting, so consequently you won't get this wetting away from the termination. You can also get this same phenomena take place if you're soldering, which you really shouldn't be now, tin lead parts. If you were running a lead-free process and you're running lead-free paste and reflowing, of course the tin lead leads are going to reflow first, so a quantity of the solder is going to tend to wet to those pins prior to anything else on the printed circuit board. It's fairly uncommon to find tin lead parts today. You know, the majority of all parts that are supplied and plated are tin, and that's the vast majority of the industry and what we see. But again, wicking can be an issue. Again, it can be a balance of heating, but think of the process you're running as well. The wetting indicators, again, are not really a defect, but a lot of people don't use this technique when it's such a simple thing to do. And here I just show you an example, first of all, optically, of a wetting indicator. And a wetting indicator is just making life easier for inspection personnel and myself as an engineer. All you're doing is on the corners, edges, and possibly somewhere in the center of a package, you change the pad shape slightly. You make the solder wet to a different position, so it changes the shape, and it just makes it easier to inspect. So in the top left, I show a ursoscope, Optilia type view of a BGA joint, which is slightly changed. And on these X-ray images, I've done exactly the same thing, and you can see the difference between the two I've circled here. One is wetting further than the other. And this gives you an indication that perhaps the wettability, solderability of the board is better. But again, the idea of this is to aid inspection to make it easier, particularly on a low-tech or low-cost X-ray system. Now, hopefully, most companies don't have mixed processes with tin lead balls or lead-free balls and a tin lead process. But these are typical examples of what we saw during the transition to lead-free technology. I have to say, in all honesty, that the one on the left-hand side was a perfectly good joint. It never ever failed after quite a few years in service, but it didn't look right. And it's clearly what's happened is the tin lead solder has soldered to the high temperature ball and made a joint. But then again, what's different between that and a typical high temperature ball on a ceramic BGA? We have a high temperature ball, we soldered to it with tin lead, it will look exactly like that. On the right hand side, you can see some misalignment and the solder is wetting to the ball, possibly a little bit of wettability issue on the balls themselves. But again, hopefully you're not using a mixture of tin lead and lead-free today. Now just an opportunity for another survey, and this third survey is looking at reflow and reflow issues. So if you just take a couple of moments to select which one of these you feel is the biggest issue in your manufacturing environment. So I'll just remain silent, but if you can just select one of the topics you see there that you feel would contribute or could contribute to the most of your process issues. I'll just wait till I've got over 90% and then I'll close the survey. Excellent. That's over 90%. Thank you very much. We just got one more survey to come a little bit later on. Now, non-coalescence of solder paste, or what generally in America is called graping. And this is where we've either run a low residue paste in an air environment and we've exhausted the natural fluxing medium or the material available to aid reflow. And that's probably the most common reason for this particular process issue when lead-free was first introduced. A lot of people were trying to run profiles which weren't perhaps appropriate. However, in the early days, the transition between tin lead and lead-free, it was kind of around the time that a lot of people were talking about direct, straight up ramp profiles and down, so straight up and straight down, just like a tent. But in the real world of manufacture, a lot of processes and a lot of companies' products, it was not possible to run profiles like that. You just get a board with nothing reflowed on it. It just wasn't going to work. So having that step profile improved it, but where you've got an ultra low residue paste, then you get problems. What we've seen over the last couple of years is where we're looking at ultra small deposits, like on very, very small CSP type packages or 01005 or the next generation of packages, we've seen this again. So with vapor phase, you don't get it. In air reflow, you can get it. In air reflow, but with nitrogen, it's less likely. So again, you've got to look at the capability of your solder paste material for your process, but also the smallest deposit you can actually get away with successful reflow without this particular phenomena. Now, incidentally, this particular example, I microsectioned. It was a perfectly good joint, but I wouldn't have accepted it as a quality guy, and I'm sure a lot of quality engineers wouldn't have done, because all the paste particles haven't coalesced into the volume of the joint. But it has reflowed, and I thank whoever dreamed up the idea of graping. I used to call it spotting or warting in the UK, but obviously somebody in the US came up with the term graping for this particular defect. You also, and we have seen it ourselves, during the use of some of the more exotic materials, tin zinc, tin bismuth, solder paste materials, you've got the same sort of thing. These materials are not ideal to try and reflow in an air environment, and you could get this graping effect, non-coalescence of paste in exactly the same way. Now, I mentioned about the tin bismuth materials because the tin bismuth materials are becoming popular again, for low temperature work. And if you have experimented with the low temperature solder pastes, again, you can see this particular issue. However, generally speaking, I find that most of the materials used in the industry tend to work pretty well, and most of them I'm using with intrusive reflow anyway, so I'm using a large paste deposit, not a small paste deposit. So I generally don't seem to see the same issue. Now, secondary reflow as a process issue is, or used to be, where we reflowed something and it was the boards had components on top side and you were wave soldering or selective soldering, and the components reflowed again, and if the board warped or twisted, the joints separated, as you see in these types of examples I show here. However, in these examples, what we're actually looking at is soldering with lead-free solder, but the terminations were actually coated with tin lead. And one of the things that some engineers forget about is that if you introduce lead to a lead-free joint, the actual temperature at which it reflows the second time round is lower. So if you've got a lead-free joint on the top side of a printed circuit board and it has got some lead in it, if you introduce it and have a higher preheat, which you typically do with selective and wave on a lead-free process, potentially the top joints can reflow. And if you will look at it in a little bit more detail, when you separated the pins away, you might see an image like I show you on the right-hand side. And this is the bottom or the cup of the solder joint where this J-lead termination has been literally separated from. And the clear indication here, this is a liquid separation. There is no brittle fracture. So we haven't broken this joint. Literally, it reflowed again, and you could just lift it out. There was a separation because of the lower temperature of the part. Now, cracking of components, generally speaking, I don't see much of these days. I still see it occasionally on BGAs. This is just an example of cracking, all due to moisture. This is an example of popcorn cracking. Again, same reason, we've got moisture which is present within the component. But most companies tend to control their component inventory and their PCB inventory well enough to eliminate these particular problems. However, if you're going to be reworking product that's coming back from the field, reworking product that's been on the shop floor for a period of time, which hasn't had the same control that the components will have had in their original packaging, then you need to pre-bake to make sure you're not introducing a problem at a later stage. And popcorning is a well-found term for this defect, because if you are reworking and you stand very, very close and be very quiet around a component being reworked, you can actually hear it pop. Trust me, I'm a consultant. Now, failures of components, again, can occur and not necessarily to do with the solder. So in this example, this is a lovely example of where components have failed, but it's the solder interface on the component itself. The termination has separated. This is due to an inappropriate plating on the component. Now, during AOI and inspection, the solder joint looked perfect, but it's the plating on the pin which was the problem, and the barrier plating wasn't properly in place on that part. Now, pad cratering is a defect that hopefully not too many people have experienced, but literally it's the pad separating from the PCB. And it's all to do with the mechanical force applied to a joint, a component, or the board during the assembly operation or after the assembly operation. Now, a lot of the high temperature laminates don't have the same adhesion of the copper pad to the substrate, and also the epoxy resin used within some of these materials is much harder. So any of the energy literally is going into that interface rather than being absorbed by the solder joint. And this is just an example of me using die and pry to investigate pad separation or pad cratering. Again, die and pry is a simple technique, and it's a very useful failure analysis technique to learn so you can do this yourself. I do this for customers all the time, but normally what I do is after I've finished doing the exercise for them, I train them how to do it themselves, because it's fairly cost effective to do, and it's a good learning experience to learn how to do it. Hip hop, head in pillow, head on pillow. Yes, you can see it. We know we've experienced it. And here's an example of a couple of BGA packages, sideways views that you can see present. And here are a couple of examples on X-ray. Now, X-ray, if you've got three-dimensional X-ray and you can look at an angle, or you've got the definition of the X-ray to be able to look at the ball and the outline of the pad, you can start to see this defect. A lot of people said you can't because we're looking at lead-free and lead-free solder on the pad and lead-free ball. But again, it's all about the definition and the capability of turning the package. Again, most X-ray systems have the capability of checking these out, and certainly with the introduction of CT. What's the most common reason for this? Well, a lot of people talk about the paste exhausting, which is very true, the activity, the wettability of the paste exhausting. However, the crucial thing is the warpage of the component. So one of the ways we overcome that is actually adding perhaps more solder paste to selected areas on the printed circuit board for BGA packages. Or certainly in corner areas, sometimes what we do is increase the pad dimensions in those areas. So again, there's a few tricks that process engineers use to overcome the variability of the component. And packages do warp, there is no question, and you can effectively measure it. We get the same thing, or potentially get the same thing, with POP, package on package. And here's an example of some open terminations. And on the bottom example is some of the second generation POP packages, which some of you will be familiar with. And here I show the same basic fault, where we've got 2 terminations made and we've got 3 opens. And these 2 close-up views I show you on the bottom of the slide here is the indentation formed on the solder ball when we're doing investigation afterwards. So it's all about warpage. It's trying to control the warpage of the component, or add more solder paste to take up that variability in height that you may have between certain terminations. And after a while, if you've done some experiments, you'll be able to determine which bits are always open, where the package is warping, and then compensate for it with your paste volume. Now, just a few simple examples of solder joint failures. Top example, we've got the component separating from the solder joint, and we can see outgassing. Now, if you get a lot of outgassing and a lot of voids, very fine voids at the interface, it does reduce the mechanical strength of the joint. It may not actually cause it to fail, but it can reduce the mechanical strength. In the bottom example here, we see an example of de-wetting. That was a perfect solder joint, but when it went through a second reflow operation on this through connection, all the solder wetted back to the pin and obviously decreased the amount of solder around that position. These 3 examples are thermal expansion failures. And basically what we've got here is a single-sided board, and the solder joint is formed, but either the pin was expanding and contracting against the laminate surface and literally pulling it out of the solder volume. So if you've got the wrong hole to lead ratio, this will happen quicker. If you've got the right hole to lead ratio for the same design, it will take longer. If you add more solder to the joint, it will last longer, but inevitably it will still fail at some point. This example is kind of a combination of mechanical failure and then obviously having a high resistance causing it to burn out. So what you can see here is a very heavy component was actually vibrating on a printed circuit board, and in time it actually started to form a crack around the termination, and then in time, because of the operating voltages, it actually burned out the printed circuit board. So it's all about the weight, the component, and its capacity on the board, and not using the right design rules. Here we see a couple of examples, classic LCC packages, all down to thermal expansion. And if you get a lot of thermal expansion on any printed circuit board, even some of the smallest of components like LGA QFN packages, they will fail in time. Now, if you get 1,000 cycles or 2,000 cycles, is that adequate for what you want? In a lot of occasions, yes, it is. In certain applications, it isn't. So you've got to appreciate that if you subject products to temperature cycling, it will have an impact. It's just understanding when that impact is going to impact the reliability of your product. But same with vibration, we can get similar types of failure. And what you can see here are 3 examples of cracking on this type of package, which could be created by temperature cycling, most common, but also it can be created vibration. Now, this example is temperature cycling, but it's actually to do with conformal coating. And what actually happened here is somebody applied conformal coating, which is fine, but they filled up the complete area underneath the package, and during thermal cycling, the conformal coating expanded and contracted to such an extent that it actually caused the solder joints to lift. This is something that I was shown at an exhibition in the US when I was doing some X-ray work at the show. Again, it's not uncommon to fill completely underneath SO packages, but you need to know what material you're using and the thermal expansion coefficient of the material for any conformal coating application. Generally speaking, as people tend to move more to spray coating, selective application, as opposed to dip coating, you tend to get less material. So consequently, perhaps this would be less of an issue if you were using those processes as opposed to dip, but you must always check the conformal coating material you're using. A couple of other examples. Now these are, in my opinion, the middle one and the bottom one are not really failures. These are what you can see. So if you're running a tin silver copper soldering operation, be it reflow or selective or wave, and you're using a high silver content material, you can get this what people refer to as tearing, where between the grain boundaries you're getting tear lines within the bulk of the solder. And this happens more commonly than you might think, but because nobody normally inspects at this high magnification, you don't see it. I have had this on quite a few processes that I've examined for companies, and in all honesty, there's two ways around it. Change the alloy. So if you're using tin copper or you're using tin copper and much less silver, you won't have the issue. But in all honesty, I've never ever seen one fail. Bottom example is fillet lifting, where the solder is actually lifted from the surface of the board. And again, you'll see both of these types of lead-free related process condition highlighted within IPC 610. So again, you can take your lead from that on the criteria that you might want to set. Final survey of this particular session is related to automatic inspection. And I simply wanted to ask you where the process, or what position in the process that you feel is most of benefit to you. So again, I'll give you a few moments to take the survey, and when we get over 90%, I'll close the survey. So just take a few moments to select your answer. Okay, that's great. We're over 90%. So thank you very much for participating in this last of the surveys on the webinar. Now, one of the other things I wanted to highlight to you is we have a lot of information that we've created over the last few years. And one of the things we mention at the SMTA International show is the MPL defect database. And this is an online database, but we also include all of our reports. And there's probably about 150 reports on there that you can download on sort of every conceivable topic related to electronic manufacture. Most recent reports are on board delamination, CAF formation, and of course more recently on high temperature solder alloys and some of the work we've been doing there. So again, if you're interested, it's worth visiting the website when you get a copy of the slides and just downloading the reports. They're free of charge, they're provided by MPL, so please make people aware of it, and if you feel there's a value, then pass it along to a colleague. Now, the defect database, for those of you who are not aware, is basically an online resource which is available sort of 24/7, and all you need to do is select what area of interest you have. Before I mention the database, I just thought I'd let you see some of the survey results that we've seen previously when we've been doing webinars with MPL. And this sort of gives you, and of course you'll get these results plus the new results after the webinar, but this just sort of gives you an idea of where people are having issues. And it'd be nice for you to compare these with your own issues in manufacture and see if they are also true. And if you look at the printing, this is basically the same sort of question that I asked on our survey. But again, you can look at this and compare the results that you gave to the results that we've had in previous survey. And the same is also true for inspection. So back to the online database. Basically, all you need to do, if you're looking for a particular problem and a solution, you just select the topic of interest. So you look at the process, the solder alloy, defect location, volume, production, application. And then when you've done that, what will happen is you'll get a load of pretty pictures on defects related to your search or related to the topics you've selected. And if you look at one of these and this looks like the problem that you're looking for, all you need to do is click on the picture or the word, and you go to a page which shows you an example of that. It gives you a description of the problem and corrective action. You can also click on the screen and go full screen and print this out along with the description and pass it on to a colleague. So it's a defect database that the more people that add to it, the better it becomes. The more information we add to it, the better it becomes. But it's certainly a resource which a lot of companies use as a training aid and also a reference in manufacture. And where they have problems that are not featured or they haven't been able to find a solution for, they normally send them in to the defect database for us to have a look at. So just to summarize where we are, this webinar is all about informing you, telling you about process issues, highlighting some particular issues, but also telling you about what we're doing at SMTA International. You can find out other information about what we're doing during the show. These are our partners, which you can visit during the show. Of course, obviously, you can contact them direct yourself if you've got a particular question you wanted to ask. These are the two workshops that I'll be running during the conference, and I'm actually doing these both on my birthday. So it'll be kind of neat. Hopefully somebody will bake me a cake or bring me something along to eat. But seriously, if you're interested in either of these two workshops, you can go online to the SMTA website and book one of these workshops. I also was volunteered to do a presentation at one of the free sessions because unfortunately a speaker couldn't be there. So I'll be joining Chris Shea and Greg Wade to give a presentation on process defects. So again, if that's of interest to you or some of your colleagues that are visiting the show, may be able to check that out as a free session. So finally, what I've done is I've basically talked about the process that we'll be running at SMTA International. I've talked about common process defects and some of the causes and cures, and hopefully I've presented you some alternative issues or alternative solutions to problems. Because quite often we find something is a problem and we feel that we've got the root cause, but it's not always the root cause. So always sort of look at something outside of the box. Always when you're solving a problem, when you think you found the root cause, put the process back to where you had it and see if the process problem is still there. If it reoccurs, it will reoccur again and again and again. So the key thing is making sure you found the root cause of any problem within your production process. So, as I said, I'm just going to take a couple of questions now. So if you've got a couple of questions, I'm more than happy to answer them. But obviously, I'll be spending most of my time at the show answering questions. There's a question here about vapor phase. Is vapor phase still used? Yeah, this is from Saeed. Yes, absolutely. Vapor phase sales grew something like 10 or 15% during the introduction of lead-free technology. And in all honesty, if I was running a small contract manufacturing facility and I was doing tin lead and lead-free, I would buy vapor phase. To me, it's a no-brainer. You use either 230 boiling fluid, 240 boiling fluid, and you can reflow tin lead or lead-free in those. If you use a 230 boiling fluid, you can reflow successfully tin lead and lead-free, and in most instances, you'll still be reflowing at a temperature which is lower than you probably reflowed with your convection oven to start off with. So that's the beauty of vapor phase. And originally they were very expensive to run. I used to have two, and it used to cost me a fortune to maintain. Nowadays, the amount of fluid you're losing during the assembly process is minuscule. It really is very small if you run your process correctly. And also, if you compare, actual running costs, the energy costs between a large convection oven and a similar vapor phase system, the running costs are actually lower as well. Next question: what is the best location to do inspection? Personally, I think nowadays, if you're doing standard simple SMT down to 20 thou pitch, you don't really need to have volume measurement of solder paste. I'm sorry if I've upset anybody. So if you're doing standard SMT, but when you start to go to smaller than 20 thou pitch, when you're starting to go down to very small passives, down to 0201 or smaller, and also you're doing LGA, QFNs and small CSP packages, then I think that 2D inspection, so just coverage of pads, is not good enough. So you need to look at three-dimensional inspections of SPI. If you're going to do inspection on boards that after a reflow operation, then that seems to me to be the area that I would investigate more than anything else. Next question: how can you run vacuum in a vapor phase system? It's a good question, Mel. Basically, what you do is you obviously have to have a machine with vacuum capability. That's the first thing. But basically, what happens is you, where the boards are supported, you're enclosing that particular area in a vacuum. So the solder is in a liquid state. You're enclosing that particular area within a vacuum. You're pulling, obviously, and changing the vacuum within that area. Literally, the voids separate out. You separate that cage around the boards and the carrier plates, and then it exits. It's, from an engineering point of view, it's more complicated, both on convection and vapor phase. But most of the machine manufacturers have used these machines quite a lot. One particular machine manufacturer actually creates the reflow in a vacuum, so everything is in a vacuum. So your board goes in as a batch system, but you can still run, sort of 15 or so boards, small boards, in a vacuum. And your cycle time is not significantly more. It may be a 5-minute cycle time as opposed to a 3-minute cycle time or 4-minute cycle time in a convection oven. Even for 04 only after reflow. I would. This is with regard to inspection. I would have said that with 0402, your yield should be good enough today. You really shouldn't need to check 0402. If you've got 0402 lifting or tombstoning, it's either the pad dimensions were not right to start off with, or the volume of solder paste is excessive. Those two things are the key thing which affect small passives, but particularly 0402 in lifting. Certainly that's my experience, and that's in vapor phase or convection. Okay, so just a reminder that we'll be sending out links to this recording to pass on to any of your colleagues that couldn't attend, and also we'll be sending out copies of the slides so you can pick up on any point that you want to. So I'd like to thank you for all attending this particular webinar. I'll be sending out the material later on this evening or tomorrow morning. I hope that you found it of interest. Hopefully you might consider coming along to one of my workshops or attending SMTA International to visit our special feature area on solder paste print and reflow within SMT. Thank you very much, and either good morning or good afternoon to you all.